to Grad Slam. Thank you so much for coming and being here and supporting our graduate students and our postdoctoral associates. Really appreciate your presence today. My name is Carol Giannetti. I'm the Vice Provost for Graduate and Postdoctoral Programs, and it is my great pleasure on behalf of my office to bring you this competition today for the best 3-minute talk presented by a graduate student or postdoctoral associate. And I wanted to say that these 11 scholars have been working very hard for weeks to really perfect beautiful talks about their research designed for a non-specialist audience so that we can all understand and appreciate the amazing range of research that is occurring on this university and that these graduate students and postdocs are doing. So in order to prepare these scholars for that, we have been able to provide them with a number of workshops on topics like how to structure an effective academic presentation, stage skills for academic presenters, effective use of PowerPoint slides, and they've also been able to access one-on-one coaching. So they have really worked to perfect these talks today, and I think you are going to just really be amazed by what they can do. Okay, this is a competition, and there will be prizes given out. People's Choice Prize will be $400. The runner-up from the judges' selection will be $600, and the grand prize is $1,000. Okay? Yeah, everybody likes that. Okay. So a bit about People's Choice Award. You should each have been given a ballot when you came in. And you must see all 11 talks in order to be eligible to vote. So you can't just wait for your friend to give a talk, vote for them and run out. Okay, you have to see the whole competition to be able to vote. That's one of our rules. Okay, so at the end of the competition, you can check the box on who you think gave the best presentation. We will be collecting those ballots, tabulating them, and it'll be based on you, the audience, who gets the People's Choice Prize. In addition, we have our distinguished panel of judges who will be ranking each talk based on a predetermined scorecard. And it's important to realize that what they are giving scores for is not the research per se, but the quality of the presentation. So you can have a terrible talk on how to cure cancer, and you can have a brilliant talk on 18th century French literature, and our scorecard is going to give that to the literature person above the person curing cancer every day, okay? Because what we want to do is to make sure that everybody can effectively talk about their research in a way that is interesting and engaging for a non-specialist audience. So in particular, the criteria that they are being judged on are clarity, organization, delivery, effective use of visual aids, the extent to which the topic and its significance is communicated in a language appropriate to an intelligent but non-specialist audience, the articulation of why the project matters. This is so important for all academics to be able to talk to others about why their research is important. And finally, engagement. Did the speaker spark your intellectual curiosity and make you want to learn more? In addition, this is a 3-minute talk, and so each talk is carefully timed by our timekeeper, Ashik Rafi, and at the end of 3 minutes, he will ring a bell. Okay, if you hear that, you know they have hit their 3-minute mark, and every few seconds they go past that, they rapidly lose points. Okay, at this point, it is my pleasure to introduce our distinguished panel of judges. Senior Advisor and Assistant Dean of Student Affairs, Aisha Al-Nakbi. Visiting Associate Professor of Practice in Literature and Creative Writing, Gregory Pardlow. Senior Assistant Director of StartAD, Hannah Barakat. And our Director of Pre-Award and Research Development, Kathleen Furr. And I just remembered that I had forgotten to pick this up, and I was supposed to do that. Since you can only see the back, now you know what they look like from the front. Okay, so at the end of each talk, the judges will be filling out their scorecards, and at that time, I'll be chatting with the scholars and the presenters. But if you have questions that have come up for you when you're watching these wonderful talks, make sure to make a note of them, because at the end, after everybody's gone, we will invite all of the presenters up on stage for Q&A with the audience. So be sure to take advantage of that opportunity and ask questions. Finally, the last thing I want to say is this. Please take a minute to silence your mobile phones, because these people have been working really hard to put together these brilliant talks, and we don't want to throw them off their game by having somebody's phone ring in the middle of it. So if you would do that. We are going to move now, get the competition started to the presentations. These are the names and titles of the presentations and the order in which they will go. So, with no further ado, it is my pleasure to introduce our first speaker, Wijud Awad from the Department of Chemistry, who will talk about crystals, ones that actually crystals, ones that actually heal. I'm sorry. Okay, come on up.
Given my topic, I kind of wish it was about French literature, like Carol said, because it's about cancer, but okay. Don't start timing yet, please. Okay. I have lost a loved one to cancer. And I know I'm not alone. By a show of hand, how many of us here today have either lost someone to cancer or know someone that's struggling with cancer? Thank you so much for sharing, and I'm really sorry about everything you're going through. And I would like to take a couple of seconds to show our respect and solidarity. According to the World Health Organization, cancer is the leading cause of death in over 60% of the countries worldwide. Half of these numbers are accounted for by Asia alone. We're talking 20 million people diagnosed with cancer, 10 million people dying of cancer every single year. Unfortunately, cancer is one of those diseases that doesn't discriminate between a baby, a child, a parent, a friend, or even a pet. It is so aggressive and mutates so much against the traditional treatments that most of them are rendered futile. Majority of the anti-cancer drugs work by interfering with organelles or chemical pathways, so it doesn't really target the cell as a whole. The problem with this is it ends up getting rid of everything in sight, good and bad cells alike. This leaves cancer patients often tired, weak, and with low quality of life, not to mention forcing their loved ones to slowly watch their transition into the person, slowly forcing their loved ones to watch them transition into a shell of who they used to be. Now, I'm not here to talk about, I'm not here to play the game of chance with pathways and organelles. I'm here to get rid of cell as a whole, with a literal bang. Imagine if I were to tell you that the secret to curing cancer or getting rid of it is crystals. And no, I'm not talking about crystals that people claim can tell you the future, or ones that if you walk around with a moonstone, it can heal you in 4 to 5 days. I am talking about tiny, teeny crystals that are not even visible to the naked eye. Let me walk you through my process. I take these crystals and then I wrap them up in a coating that cancer cells really like to eat, like you can see over here. Once these crystals are taken by the cell, I shine light, which causes the crystals to explode, rupture the cell, and cause it to die. At this point, you're probably wondering, Wijud, are you really talking about making many explosions inside my body? And how can you be so sure it's only the bad cells? Well, the answer is quite simple. That coating I just spoke of is so specific, it can only bind to cancer cells. Think of it as a lock with only one specific key. My work is founded on the same principles surgeons use when they're tackling a tumor. They go in and they remove the tumor and the surrounding tissues. I do the same exact thing, but on a cellular level. I get rid of the cell so that it has no chance to mutate against our treatment. To put things in perspective, in the 3 minutes it took for me to deliver this talk, 35 people passed away of cancer. It's one of the fastest growing diseases, and unfortunately we're in dire need of things, out of the box thinking and groundbreaking research such as my own. And today we're fighting with crystals that actually work. Thank you.
Right, thank you. Well, that was a great example of a how to cure cancer talk that was just wonderful. So thank you so much for that. So, Weijia, tell us a little bit about yourself. So where did you grow up? Where did you go to college?
I grew up here.
Okay.
Born and raised in Abu Dhabi.
Abu Dhabi, all right.
Yeah, I think a lot of people are on the same boat. I went to school also in Abu Dhabi. My family is originally from Egypt, but they've been in the Gulf for over 30 years due to trade. So yeah.
And where did you do your undergraduate work?
Abu Dhabi University.
Abu Dhabi University.
Your neighbor.
Yeah, excellent, excellent.
And competitor.
Excellent. So this is so interesting to me. It seems like it's a Trojan horse kind of a strategy.
Exactly. That's exactly what we're thinking of. We want to sneak things in and get rid of it.
So did you read Homer as a kid?
I just bought a copy recently in the sale in the bookstore.
Very good. It's really worth reading the Iliad for sure. So it's so interesting about the light. So why is it that how does the light activate the crystals and cause them to explode?
Okay, so the mechanism behind this is you have these crystals which have a particular structure. So once you shine the light, it undergoes a chemical reaction, right? And this chemical reaction, basically what it does is it causes so much stress in the structure that the only way it can release it is by exploding. So yeah.
Yeah, fascinating. So tell me something about yourself that your advisor doesn't know, your supervisor doesn't know.
Until he sees this recording, he doesn't know that's the presentation I chose to present. I have multiple projects, so.
I guess so. Wow.
But this one is my baby, so.
So is this going to be your doctoral dissertation?
Hopefully, yes.
Hopefully, yes. How many years do you have still?
I only have a few months to go. Woo!
All right. And then where do you plan to go after that?
I am not sure yet. Maybe academia, maybe the industry. But you know, I'll go with the flow.
Seems like you have a lot of options. So thank you very much, and we'll move on to our next talk. All right, onward. Our next presenter is Fairouz Abu Ibrahim, again from the Department of Chemistry, and her talk is entitled, Why Temperature and Humidity Sensing Really Matters.
Thank you.
Yeah.
I want to thank Wujud for the inspiring presentation before. And I'm hoping to take you on a more of a soothing journey. So that's we can. Sorry. So imagine with me, 50 years from now, you are living in your house. You feel much more comfortable and cozy. Why is that? In our future smart homes, the indoor ambience would be so up to our standards that we will feel as if we are constantly being hugged. No, this is not daydreaming. This is because all of the implemented sensors around the house are automatically monitoring and adjusting humidity and temperature levels to our convenience. Not only that, sensors will be implemented in buildings for the sake of preventive maintenance. They will be implemented in agricultural soil for a live monitor for temperature and humidity, in the food industry and processing, in pharmaceutical production and delivery, in chemical labs, basically everywhere. However, most of the sensing devices and technology today heavily rely on amorphous polymers. These polymers literally look like this from a chemistry perspective, like an entangled hair comb. Very little can be known about how these materials actually work and sense the humidity and temperature. In my research, we work on dynamically controlling the reaction during the formation of these materials. We try to get a sense of organization of this material. Through this organization, we can actually see, study, and understand why one specific material could be what we are looking for. And to get a sense of the numbers, as per the expert market research, the humidity sensing market was estimated around $6 billion last year, and it is estimated to increase to around $13 billion in the upcoming 5 years. So by smart engineering, we intentionally designed this material to change color from yellow to red as a direct, instant, and a visual indication of the temperature and humidity surrounding it. This material is so versatile, so it can glow in the dark, in freezing temperatures, in life-threatening conditions, and it can be applied as in firefighters' clothing, but it can also sense the humidity, and the humidity as in sweat level, and the temperature as in a physiological temperature, to be implemented in future smart textiles. So let's go back to the beginning. The future for my research is not in 50 years. The future for this material and my research starts now. Thank you so much.
Thank you for that wonderful talk.
Thank you
so
so much.
Tell us about yourself. Where are you from, and where did you do your undergraduate work?
I'm from Lebanon.
Uh-huh.
I've graduated from the Lebanese University.
Uh-huh.
So it's the governmental university.
Uh-huh.
And then I got a scholarship to the American University of Beirut to complete my master's.
Uh-huh.
And this is where I got here to complete my PhD here.
Uh-huh. So how did you learn about NYU Abu Dhabi and the global PhD program?
So actually, my PI, he was visiting AUB, giving a talk about what I actually work on now.
Uh-huh.
I got so inspired, and I went and talked to him and asked him a few questions.
Wonderful. That's so often how these relationships really get started, is by faculty going and giving talks and really doing that outreach.
And inspiring.
And inspiring other scholars to follow in their pathway. So that's wonderful. This is really interesting research. I've never heard about anything quite like this. So this falls under materials science, right?
Yeah, under like a smart materials. These materials are kind of responsive by themselves. This is why they are smart, to everything that is surrounding them. So it's either like the temperature, the pH, so they can give us any type of response as a as a response to a change in their external surrounding.
So if you have something like an article of clothing, it seems like both the ambient environment as well as one's physical body might be impacting the heat and the the humidity. How does it differentiate those two things?
Yeah, I think it's just a futuristic view, just to get a sense where these type of materials will be applied. But of course, like, there are a lot of things that should be taken into consideration. For example, like this, the surrounding, humidity and temperature. But basically, like, the mechanism should be by, like, it should be touching the skin, so that there is like a transfer of the water molecules inside the structure, and some hydrogen bondings would happen in the structure so that it can change its color. But yeah, of course, like, there are a lot of consideration to be taken, like, once developing this.
Well, if you get a chance, please figure out how to keep my glasses from fogging up when I walk outside. So thank you very much.
Thank you so much.
All right, our third talk today is by Yusra Ajouao from the Department of Biology. She's a postdoc who will be talking about unraveling the secrets of healthy aging.
Thank you. Okay. The air you breathe, your diet, and your lifestyle choices have a profound impact on how your DNA and genes work through what we call the epigenetic code, which acts like traffic lights within your cells. Now imagine that your DNA is a complex road where the epigenetic code controls red and green lights, allowing some genes to go and others to be stopped. In case of emergencies, such as injuries, this epigenetic code springs into action, activating genes implicated in repair while silencing useless ones in this process. This code is constantly rewritten with your life decisions and has long-term effects, especially on how you age. Let's face it, we're all getting older here, right? But don't worry, you are not alone. The global population is rapidly aging, accompanied by unprecedented challenges in healthcare, as aging is the main risk factor for many diseases. The solution? embracing healthy aging. But how? By understanding the root causes of biological defects that emerge as we age. Alterations in the epigenetic code have been proposed as one of the main contributors to unhealthy aging. So for my project, to unravel the role of the epigenetic code in aging, I have chosen to focus on the largest organ inside our body, the liver, often referred as the guardian of our health. The liver is unique. It performs over 500 vital functions, and it is the only organ capable of regrowing itself after injury through regeneration. And this ability is lost during aging. Using a mouse model of liver regeneration, my team discovered that the epigenetic code is actually the key to enhancing liver regeneration. And by inducing changes in the epigenetic code of the mouse liver, I noticed a slowdown of the aging process. Amazing, right? Which means by just changing the epigenetic code in the liver, it might have a huge impact on the overall aging process. My end goal is to uncover key factors of this epigenetic code that are responsible of reduced regeneration during aging. You see, the real challenge is not the aging itself. It's aging in an unhealthy manner. On average, our time in good health is 16 years less than our total lifespan, which means that each of us present here today is at risk of spending our final and precious 16 years in an unhealthy condition. So my wish for all of you is, may your good health be as long as your life. Thank you.
Thank you, Yusra. What a wonderful thing to be able to work on and, talk about doing research that has an impact. Think about all the people that could potentially be impacted by your research. It's just wonderful. So I'm very, very happy to hear of this work. So tell me about yourself. Where are you from? And where did you do your graduate work before you got your postdoc here?
So I'm Moroccan, but I was born and raised in Brussels, Belgium. And I did my master's degree and my PhD in Université Libre of Brussels in Belgium. And then I joined here for my postdoc.
And how did you end up in Abu Dhabi of all of the various places? What drew you to this university?
Actually is the fact that NYU is like a high-rated university with very good quality science, and more like here in Abu Dhabi, it's a Muslim country, which I think matches all my, my criteria. So high quality science, where I can be like comfortable to do my work.
Oh, perfect. Well, we're so happy to have you here. So this is really amazing stuff that you're doing. Can you tell us about how you actually changed the epigenetic code?
Yeah, of course. So we are using knockout mice. So we are basically take out a gene from the genome of the mice, and this actually is an epigenetic modificator. So by taking out this gene, we're just reshuffling the whole epigenome. So it's like an unbiased way. We just take out an epigenetic modificator, and we see like changes in the epigenetic code.
I see. So you remove a gene, but you don't like add another gene back.
No, because like this gene is known as an oncogene.
Okay.
So it's already like known to be not good for our cells. So there is like some drugs that can target this protein actually, but it's not like. It's under research still.
So I hadn't realized that the liver played such an important role in aging.
Yes.
And I had heard about that the livers could regenerate themselves, but it's really interesting to me that then this can then have these other effects because the liver is functioning well.
Yeah, because the liver is like the organ that filter what we eat, the drugs, the toxins, everything. So if it's not healthy, you will like stay with all the bad things in your body. So that's why he has like so much, that's why the liver is very important, because it's like the filter. Everything goes through the liver and yeah.
Fascinating. Okay, thank you so much.
Thank you.
Okay, our next talk is by Kunpal Ali from the Department of Electrical Engineering, another postdoc, and it's entitled Meowing Our Way into 6G.
Hi. Cats are some of the most wonderful, sassiest, and smartest animals. They can communicate. Our family cat regularly meows us into getting him whatever he wants. And cats can sense. They have super sensitive whiskers that allow them to see well beyond the vision of their eyes. Now, I work in wireless communication, the 4G or 5G in your phones, and currently we're working on 6G. Without me, your Instagram doesn't work and your Talabat doesn't work. So clearly, my research is important. Now, you're probably wondering what that's got to do with a cat, and we will get there. Now, what if I were to tell you that your access to your cellular internet was about to be split? I bet not a lot of us would be happy. And this is because as technology is progressing, not only are we interested in using our gadgets to communicate, but we also want to sense with them. I'm sure all of you have heard of things like self-driving cars and smart homes. All of these super cool technologies that are futuristic depend on making our surroundings alive. And this requires the ability to both communicate and to sense. Sensing, just like communication, requires signals, the magical invisible waves that help us receive important Instagram videos throughout the day. And while communication and sensing use the same kind of signals, for decades, they've been advancing independently. Now, most of the world's communication happens in the shaded part of the spectrum here. And the spectrum is limited, but our communication needs are only growing. Wanting to increase sensing means that we're gonna have to share this limited, scarce spectrum that is mostly occupied by communication with sensing. This means if we want more self-driving cars, we have less Instagram. But are we ready to share? Fortunately for all of us, my lab does not believe in compromise. We are actively working on an exciting new area, one of the next big directions of 6G actually, called integrated sensing and communication, which truly allows our gadgets to become more cat-like. With Isaac, we're designing a system that allows us to use one signal for both communication and sensing. This way, we're able to reuse the spectrum, which is limited, and we reduce power consumption, because now you're using one signal for two things. Isaac will help improve technologies like smart homes and cities, autonomous vehicles, Internet of Things. It also opens doors to using our everyday gadgets for things like spectroscopy. Imagine pointing your phone at a salad your neighbor made to check for nut allergies. In closing, becoming more cat-like with Isaac is an exciting new direction that is cost-effective, green, and will improve our quality of life. Thank you, and meow.
Hi, thank you. Hi. Fascinating. I love this stuff. So tell me, where are you from? Where did you do your graduate work?
I'm from Pakistan, but I grew up in Saudi.
Okay.
I actually ended up going back to Saudi for my PhD at KAUST, and now I'm a postdoc here.
Fantastic. Yeah. I know KAUST is a wonderful school. So.
It is.
So and then how did you end up at NYU Abu Dhabi?
I actually moved to Dubai at some point during COVID. Okay. I had family there, and then, you know, the stars aligned. There was a position here, and I ended up coming, and it's been a great experience.
Good. Yeah. Good. Glad to hear it. So do you consider yourself a cat person?
I had a cat that actually my 4th grade teacher took because the cat needed surgery, and this teacher had like a lot of pets and stuff, and I never got the cat back. And I never got the cat back, and her friend, who was also a teacher in our school, had 27 cats. And for 20 years, I hated on Mrs. Susan. Maybe it wasn't 20, it was 14 years. I hated on Mrs. Susan, and I was 22 years old. I was sitting in Istanbul with my friends, and my friends were like, dude, your cat died in surgery. And I was like, oh. And all this time, I thought Mrs. Susan had my cat. But it died.
Well, that was a story.
Yeah.
So I bet you don't think much of that cat when you're doing this particular type of research when you're in the lab. Does that?
No.
Do you have a picture of the cat that you can?
No, I don't.
Okay. Yeah, it's interesting how our needs, I mean, I think you made a convincing case here, and it's interesting to think about how our needs just continue to expand.
Yeah.
I mean, it's just astonishing when we think about how many smart devices we all have and how we use them and what kind of kind of bandwidth we need. So
5 years ago, our phones did not have the number of apps that we have right now. And it's just growing. So
yeah.
It's just growing. It's not declining.
Yeah.
So.
Yeah. So it seems like you and no, it wasn't Yusra. It was Fayrouz should get together, because it sounds like some of the stuff that you're doing can help with the smart materials, and you can talk about kind of taking it beyond. So well, thank you very much. This is a wonderful talk. So I really appreciate it. Okay, our next presenter today is Devjoy Dev from the Department of Biomedical Engineering. He is a graduate student who will be giving a talk called A Gut Feeling, Improving Astronaut Sleep with an Electric Pill.
How much sleep did you get last night? We've all asked this question. Sleep is a silent killer in our lives when it is not valued enough. Let's take an example. Very soon, daylight savings will be happening across the world in many countries, and the days will be getting shorter. But did you know that globally, there's actually a 24% increase in the risk of heart attacks when this happens, when we lose an hour in the autumn? And in turn, when we gain an hour in the spring, there's a 21% decrease in the risk of heart attacks. Isn't that amazing? Sleep is amazing, and we should cherish it, protect it. We're the only species on the planet that purposely deprives ourselves of sleep. Sleep is the #1 predictor of all-cause mortality. Quite literally, the shorter your sleep, the shorter your life. My research is looking at sleep in the most extreme environment we've ever known, in space. In space, microgravity gives very harsh health effects onto our body, including on our sleep. We get much shorter sleep than we do get down here. And this is caused by numerous different factors, such as the isolated, confined, extreme microgravity environment, deep space cosmic radiation, and also, of course, the lack of sunlight, which is our biggest regulator. And this is even a bigger question when we think about what happens when we spend longer in space and travel further in space, how these effects worsen over time, away from our protective sphere. We know ourselves that when we deprive ourselves of sleep, even just by a small amount, the next day our performance is significantly affected. So just think about if astronauts also experience that same fatigue, that can't happen at all. Not only would it mean the risk on the mission, but the risk on their lives as well. My approach is harnessing the power of the gut. The gut is this fascinating system that we still need to learn so much more about, and has this curious connection with our sleep circuitry. There's a beautiful bidirectional relationship between the gut and the brain. And so I'm working on developing on a small pill that will travel down your gut and send safely electrical impulses to the lining of your gut where there are millions of neurons, so you could stimulate them and modulate your sleep in a way that we've never done before. I'm also simulating microgravity in the lab itself so that we could see how sleep cells respond to these effects and actually control and mitigate these changes to our circadian rhythm. If we could improve their sleep up there, we could improve ours here. Sleep is a non-negotiable biological necessity that we cannot afford to underestimate. I'm convinced this will be the next frontier to GI and sleep technology. This is not just a gut feeling. Thank you.
All right, thank you very much.
Thank you.
You learned so much in these Grad Slam talks, things that you never would have thought about in the course of your life, and it's all so fascinating. So really appreciate your sharing all of this with us. So tell us a little bit about your background.
Yeah, so I'm from the UK and did all my education there in London. Queen Mary University of London, and my master's was at Imperial College London.
And what attracted you to the global PhD program at NYU Abu Dhabi?
So I was applying for my PhD at NYU, and I actually knew my PI, Dr. Khalil Ramadi, like 6 years ago, because I was in the States and I met him as a TA over there in Boston. So we kept in touch. He knew my interests, I knew his. I told him I was applying to NYU, and he was like, come join my lab. And it worked out.
Excellent. Oh, that's excellent. So how did you get interested in astronauts? How did that piece of the space piece kind of fit in to your research and on sleep and around sleep?
Yeah, so it never started with sleep or the gut. That sort of just made its way there. But for me, it was always about medical devices, biomedical engineering, and then it was actually when I went to the States that I saw that space medicine is a thing there. And I was like, wow, okay, my interests of space and biomedical engineering can actually fuse. So that's when I really delved into it more, and I wanted to become really deep into it in my thesis. So that's how it became. Yeah.
Have you been interested in trying to engage with any of the UAE space agencies?
Trying, but failing slowly. Yeah, they're hard to contact, but in the past, when I was in my master's, I worked with the European Space Agency. A lot easier to get in contact with. But hopefully, let's see.
Okay, well, be persistent.
I will.
Because persistent furthers, so this would be great. So thank you so much.
Thank you.
Really appreciate your talk. All right, our next presenter is Kamel El-Khoury, also in bioengineering. He's a postdoc who will be talking on lab-grown organs, engineering life and hope.
Thank you. Hayat, which in Arabic means life, is the national program for organ donation and transplantation in the UAE. In 2023, more than 100 organs were donated and transplanted through the Hayat program. However, that is not enough, as more than 4,000 patients are still waiting for a precious organ to be donated. And even when an organ is transplanted successfully, it will only last between 5 to 15 years before getting rejected by the body. We can solve this by creating organs in the lab from the patient's own cells. That way, there will be no rejection, and we will have an unlimited supply of organs. However, cells when cultured outside the body are just like people after marriage. They will look and behave differently. The main reason is because we cultured them on 2D hard plastic. And because our bodies are not made up of plastic, I started culturing these cells in 3D soft gels that resemble Jell-O, the gelatin pudding. And just like my mom was mixing bananas with Jell-O, regardless of the fact that I hated that mix, I am mixing cells with these soft gels. However, cells loved it, because their shape and function were more similar to the ones found in our bodies than the ones cultured on plastics. Also, how we assemble things will affect how they will eventually work. For example, if we assemble the car by putting the wheels on the roof, it will not function properly. The same is true for our engineered organs. However, organs have a very complex architecture. And to replicate that, we use 3D printing technologies that can copy and replicate the exact structure of any image we upload, no matter its complexity. So, if you visit me in the lab, you will find me chemically modifying these gels, mixing them with cells, and 3D bioprinting functional organs. And no, we're not there yet, but we're on our way. These 3D printed organs will not only solve the organ shortage problem in the next decade or two, but they are enabling us today to produce cheaper and safer drugs and to study complex diseases that we don't understand fully yet, like Alzheimer's disease. In Arabic, Hayat means life, and Amal means hope. And with a collaboration between scientists, engineers, clinicians, and funding agencies, we can give patients Hayat and Amal for a better future. Thank you.
Thank you, Camille. Wow, there's been so much about health, related to health, and it just gives you so much hope for the future to see people like you doing work like this. So thank you so much. Tell us about yourself.
So I come from Lebanon, where I did my bachelor's in chemical engineering at the University of Balamand. Then I moved to the UK to do my master's, also in chemical engineering at the University of Birmingham, where I was introduced to the field of bioengineering at the same time. So I loved that field, and I decided to pursue a PhD in the field. So I moved to France, Northeast, at the University of Lorraine, where I did a PhD in bioengineering. And during my PhD, I did 2 research mobilities, one in Portugal and one in Harvard in the States. And then I went back to France, finished my thesis, defended everything, and then moved to the south of France, to Toulouse, to do my first postdoc in the National Research Lab. And after that, I moved here to the UAE to do a second postdoc about bioprinting. And thanks to the GPPO and the mobility grant for postdocs, I was able to go to NYU as well.
Oh, excellent.
In New York. To do research this summer also.
Wonderful. It's great to know that you're able to take advantage of that program. Yeah, that's really good to hear. So it seems like one of the real innovations of what you're doing, and maybe, I don't know much about bioengineering, that's for sure, but it seems like one of the innovations, based on what you said, is this idea of moving to soft gels.
Yes.
And to sort of change that medium in which these cells grow. Was that your idea?
No, actually, that's in the whole field is using them, but I'm using a specifically modified chemically gels that we can, when we shine light, it will cross-link. And actually, that gel resembles very much Jell-O because it's gelatin-based. So we do a chemical modification of that gel, and then we mix it with cells, and then we shine light so that it's stable even at high temperatures, because the gelatin will usually dissolve at high temperatures. So it will remain as a gel, and then it has a big pore size where the cells can go in and out of it, and then they will produce their own support, the cells, while this gel is degrading. So at the end, that's why there will be no rejection, because at the end, everything will be produced by the cells, by the patient's own cells. So it's 100% compatible with them.
Yeah, that's just astonishing. That sounds like such a wonderful thing. And then tell us a little bit more about the 3D printing side of it. How do you then go from these cells that are, such a good replication of the person's own DNA and cellular structures to an actual printed object?
Yeah, so
sounds like magic.
If I want to replicate the heart, for example, I cannot do it manually. Like with pipettes and trying to do all the different compartments. That's why we use like a CT scan for the patient. Then we take a scan of his heart. We just put it in the machine, transform it as a file to the machine. Then it can replicate the exact structure of what we upload there, and it will 3D print the gel with the cells mixed with it. So it will have a fully functional heart.
I see. Wonderful. Thank you very much.
Thank you. Thank you, everyone.
Okay, our next speaker is Maya El-Sawi from the program in physics. She's a postdoc. Particle physics searches to unveil the secrets of the early universe.
Are you watching the Big Bang Theory series? Yes. Actually, I'm working on particle physics, much like Sheldon and his friends. So particle physics might not have a direct impact on our daily lives. However, it has a significant indirect effect. The scientific research we are conducting to understand our universe mechanism and structure also lead to innovation in technology in various fields, like electronics, medical imaging, cancer treatment, and particle beam therapy. So can you imagine, with all the technology we have right now, we only know 5% of the contents of our universe, which cannot answer many questions, like what is the world made of and what holds it all together? So imagine going back in time, billions of years ago, when nothing was exist, everything was incredibly hot and very tiny. Then something amazing happened. The tiny points start to expand and cool down, and this is what we are calling the Big Bang. As the universe expanded and cooled, it started to form the building blocks of our universe, atoms and particles. These particles eventually came up together to create all the matter in our current universe. And at CERN, the biggest research laboratory in the world and the birthplace of the World Wide Web, we are going back in time using particle accelerator as a time machine to recreate the early moment of the early universe. We are smashing two beams of particle with very high energy to produce 40 million collisions per second with the same condition of the Big Bang in the heart of this onion. Yes, our detector looks like a giant onion with many layers, and each layer is designed to capture the track of new particle. So you might be wondering why all this matter. Well, in 2012, we discovered the Higgs boson, the so-called God particle. And Higgs is very crucial to understand our universe mechanism. Without it, particles would not have mass, and everything would be flying around us with very high speed, making it impossible for human, planets, or even life as we know to exist. And another mysterious particle, which is neutrino, it's one of the fastest and lightest particles in the universe. It's around us, but very challenging to detect. And currently, I'm working on studying the relation between Higgs and neutrino, as Higgs gives mass to any particle it interacts with. Remember that when scientists discovered the electron, they never anticipated the huge revolution in technology that it would trigger. So, when performing such a research, we never know what groundbreaking discovery we would get when we do this study, because we don't know what we don't know. Thank you.
Thank you, Mai. So now we've going from thinking about the future to thinking about the distant past. So very, very interesting talk, so thank you. So tell us a little bit about yourself and how you came to be at NYU Abu Dhabi.
Okay, I'm from Egypt.
Okay.
I finished my PhD. I have a dual PhD degree between Antwerp University in Belgium and Egypt. And I got my PhD at CERN Studies, but with another research. I started here as a physics instructor in 2021 during COVID. And then after 1 year, I moved recently last year to be a postdoc with high energy physics group. Yeah.
So how did you first get interested in working with CERN and the amazing work they do there?
It started, I was working as Ross, an admin job related to scientific research in Egypt at the British University. And I was organizing all the events and all public talks for all speakers from all over the world to talk about CERN and giving schools. And then one time I met my PhD supervisor, and he convinced me, because I was doing master on nuclear physics. He told me, you are doing all of this for all students, why don't you go to CERN and start to work on this? So I started my PhD and finalized it on search for another thing, but recently when I came to Abu Dhabi to join my family after PhD, I was searching for an institute to complete working with CERN, because I left Egypt. So gladly I found the group of high energy.
Marta Losada. Yeah.
Don't ask me what you don't know about me.
Okay,
she's here.
I'll leave that for a private moment between the two of you. So that's fine. So, but I came from UC Santa Barbara, which has a really good theoretical physics and astrophysics, and I knew people there that spent time at CERN, and it was just amazing to hear about what this is and the stuff that they do at CERN and to learn about it. There's a man named Joan Candela who was one of the people that was really kind of deeply involved in the work on the Higgs boson.
But actually, we are doing much more, because United Arab Emirates, now it's a part of this collaboration. We need to perform some shift on the control room to monitor the performance of this giant onion that you saw, which is Atlas experiment. So last summer I was at CERN intern doing some chat for the experiment, and it's really not easy to have a stable beam of particles to have this collision.
I'm sure.
So I was really, really excited to be there with Atlas, with Emirates, not with other.
And it's a big international collaboration.
Yes.
It just must be so inspiring to be able to go and to be part of something that is that international and with everybody really working together in this common scholarly community.
It's a very nice place to work.
I'm sure that's true. So, okay, well, thank you very much for your talk. Okay, on to Nadine Hosni El-Said from biology, switching our bad genes off.
Does anyone here have a twin brother or sister? Perfect. Are you identical? Yes. So have you ever wondered why identical twins with the same identical DNA behave so differently when they grow up in their future? One might develop Alzheimer's and the other not, with great memory at 70. One might have obesity and the other is super athletic. That's because of our epigenome. Our epigenome is that interface between our environment, our lifestyles, and our DNA. So imagine the pizza slice or the apple that you eat gets embedded on your DNA. This is interpreted so differently between different people. Our DNA is like a book that gets read differently according to the bookmarks and tags that you impose on it. Also, very like music. Musical pieces are read differently by different musical instruments, giving the same musical piece of DNA into different sounds. Let's delve deeper into the complexity of our DNA, which is, believe it or not, 2 meters long, but we only know 2% of its function. Our DNA is highly tangled inside our cells. And to study its function and to make it turned on or switched on, it has to be untangled and unwound. This untangling is orchestrated by the numerous molecules and marbles, as you can see, that surround the DNA. And guess what? In the lab, we decided to remove one of those marbles. And guess what? We found Meg Ryan, not just in Hollywood, but right inside our cells. Meg Ryan is an RNA. Consider it the cousin of our DNA. And it helps turning genes on and off, particularly in bone diseases like osteoarthritis or in Alzheimer's diseases and obesity. Take alone osteoarthritis. It affects around 500 million people worldwide, around 7% of the global population. So studying Meg Ryan and trying to target it will help us develop targeted therapy and personalized medicine towards those diseases. So every time you savor a slice of pizza or a bite of an apple, or even get stressed because of your 3 minutes grad slam presentation, remember, you're feeding that to your Meg Ryan, and it will affect your future health. Thank you.
Thank you so much for this talk. It's just amazing, all of the work, again, more work around medicine, and really thinking about how to help people live longer and happier lives, healthier lives. So it's really, really amazing stuff. So tell us about yourself, where you're from, and how you ended up as a postdoc at NYU Abu Dhabi.
Okay, so I'm from Egypt. I was born and raised there. I was a pharmaceutical science graduate, and I did my master's in the American University in Egypt in biotechnology and metagenomics. And then I moved to KAUST in Saudi Arabia for my PhD. And it was there when I was on one of the conferences, and I met the postdoc that was working in the lab I'm working in now, Thomas Bennett. And this networking made me end up here in Professor Pier Giorgio Percivali's lab.
So it's really interesting to think about how important networking is. And how you use conferences as a way to make those connections. You never know where things might work out for you, based on something like attendance at a conference. So that's really, really wonderful to hear. So how did you first discover, how did you decide to work on Meg Ryan? I mean, like, why this particular type of RNA?
So actually, they are two, Meg and Ryan.
Oh, okay.
And I was interested in long non-coding RNAs, which are the RNAs that don't code for proteins, and they are those 98% of our DNA that we don't know anything about.
It's amazing.
And long non-coding RNAs have been recently, like let's say the last 20, 30 years, been starting to show the functions that they have in the cell, because definitely we don't, everything has a job to do. And the 98% of our DNA or our genome is definitely reflected into a function in our cells. So my interest in non-coding RNAs came up from there. And in the lab, we are working on like mice cell lines that don't have one of the important and structural proteins of the cell. And when this protein is removed, one of those marbles, this Meg and Ryan were very highly elevated, and this is why I decided to study them.
Yeah, amazing, amazing discovery, amazing work. So thank you very much.
Thank you so much.
Yeah. Okay, our next talk is by Shaza Karaman, also in biomedical engineering, The Dark Night Within You, Lymph Node on Chip.
Hello, this says my name is Shaza, but actually I have a secret identity. I'm Batman. And today I'll prove that there is a Batman within each of you. If the Joker attacks Gotham, Batman fights him off with special weapons to protect his city. And every Batman needs his Batcave. That's where he trains to fight and engineers new weapons. Our immune system is our main defense against diseases and works a lot like Batman. Our immune cells can recognize viruses or bacteria and attack them with weapons called antibodies. These antibodies are custom-made, specific for each virus or bacteria. And this all happens in an organ called the lymph node. The lymph node is where our immune cells train to recognize pathogens and produce antibodies. While our immune cells fight, you might start to feel sick and experience the symptoms of the disease. Currently, the best solution is vaccines, which help us fight the disease without getting too sick. But vaccines have many issues. Developing a new vaccine takes 10 to 15 years, and even after this long process, some vaccines still have negative side effects. So you either get the vaccine, if one exists, or you get infected, get sick for days, waiting for your cells to make antibodies. However, there are many diseases where we cannot risk waiting for our own cells to fight, like COVID or AIDS, or even a new pandemic, because it can be deadly to us and the people around us. So why not skip the part of getting sick? In my research, I use your own cells to make a lymph node on a chip, not a potato chip or a computer chip, but the silicon chip behind me. We can use this chip in the lab to mass produce disease-specific antibodies. Then we can simply inject them into you to avoid the use of vaccines and to avoid the risk of getting sick. Together, we can unleash the Batman within us and make the world safer for everyone.
All right, so it's clear you have superpowers.
I mean, we all do.
So tell us about yourself.
I'm Shaza. So I'm from Palestine, but I was born and raised here in Abu Dhabi. I did my undergrad in Khalifa University in biomedical engineering. Then I went to Imperial to do my master's, and I came back here to do my PhD.
Wonderful, wonderful. So it's really interesting to think about these particular chips and the idea of being able to use someone's kind of own cells as a way to be able to do this.
So actually we have around 600 lymph nodes already in our body. And the body even makes a lymph node when it needs one, kind of, in a simpler way. But we're trying to do this outside so that we remove the risk of actually getting sick.
Yeah, yeah, that sounds amazing, especially as I'm thinking about going to get my flu shot.
Yes,
and thinking
exactly.
I need to do it on a day when I can be sick the next day, and so this would like take away
that would take away.
entirely. So how big are these chips? It looked really big on the screen, but
it's actually very small, like the size. It can be smaller. But we just engineer them in the lab out of silicon. And the holes inside are made by fabrication, where we put our cells.
And have you started trying these on any organisms to test to see how they work?
Not really, not yet.
Not quite.
Yes, like many other groups try to do other organs on these chips. So they've tried that, but not the lymph node.
Okay. Sounds good. Okay, thank you very much. I think we'll move on to the next speaker. So our next speaker is Wael Saeed I always have a hard time with these consonant clusters. Abdrabbu. He's also a biologist, a postdoc, and he'll be talking about the curious life of malaria parasite. All want to age gracefully.
Thank you. Thank you. Hi, everyone. I'm going to go out on a limb. I'm going to say that everyone almost in this room have thought about aging sometime today. Whether it's a wrinkle that snuck up on you, or a white hair that snuck up on you in the middle of the night, or it's a bad joint pain that you felt in the morning while getting up off the bed, and you were like, I'm too old for this stuff. You all thought about aging, and if you didn't, I just made you think about it. Aging is a very curious process. In 2008, there was a movie that was released in theaters. It's called The Curious Life of Benjamin Button. This movie is about a guy who ages in reverse, a process that we all would love to know the secrets of. How to age in reverse, or at least to age gracefully. And we all are hungry for chemicals that can make us age gracefully or multiply more. We care about this as much as we care about having children, and sometimes even more. And we are hungry for this, whether it's a pill that you're going to pop in the middle of the night, or it's going to be something that you're going to apply on your skin just to try to make it healthy. But today, I'm not here to talk to you about Benjamin Button. And I'm not here to talk to you about us. I'm here to talk to you about an organism. A single-cell organism. One cell that causes a disease, malaria, that affects and kills thousands and thousands of children in India and Africa, more than any other age or ethnic group in the whole world. And I spent the last year and a half trying to identify and trying to find out the chemicals that this parasite is hungry for. This parasite, just like you and me, just like all humans, is hungry for chemicals that can make it grow and multiply even better. And I spent the last year and a half trying to do this, and I found it. A source of fat that would make this parasite multiply and grow more and more, while the cases and the status of these children is getting worse and worse. So I took this source of fat to the lab, and we grow the parasite with this source of fat and without it. And we noticed that the parasite grew even more and generated more offspring in the presence of this source of fat more than anything else, more than any other chemical. Apparently, this parasite needs that source of fat to apply it to its surface, much more like you and I would apply something to our skin and try to make it healthy and stay healthy. Imagine with me if I can find the way to block the way that this parasite would obtain these chemicals and block that way. We could end up saving thousands and thousands of lives every single year. But that could be the topic for the next Grad Slam. Thank you.
Wow, this was stunning. So congratulations on making such a discovery. It seems really wonderful that you've done this.
Thank you very much.
Yeah, you just want to be careful that you don't spread the fat around, right, and increase the fat, but to be able to remove it or...
Apparently we all need it. It's in the diet. It's one of the most common sources of fat, fatty acid in the diet.
Okay.
So this source of fat actually exists in the diet of these children. So the more you have it in their blood, the more their status or their infection gets worse.
So that's why the barrier is important instead. So it's not about removing the fat, it's creating a barrier that then prohibits the fat from entering into the cell.
They need it to create the fat. So the parasite, just like us, has the same system. We are made of trillions of cells, but this parasite is only one single cell, but it behaves pretty much the same way. This parasite, it needs the membrane. It needs that surface to maintain its elasticity and flexibility, and it needs that source of fat to be integrated in that surface. And if we take it away, it slows down the process of growth.
So that's what you're working on now?
That's what I've been working on for the past year and a half, and we're continuing right now. We're trying to find ways to. We're gonna start to try to block that that pathway. Yeah.
Okay, well, best of luck. You know, I wish you fantastic success.
Thank you very much.
Thank you.
Thank you. Thank you, guys.
Okay, our final speaker today is Mohammed Tahriskali from Computer Engineering. From pixels to pulses, the answer is in the doctor's eyes.
Do you know that, just like our fingerprints, our heartbeat rhythm is unique to each one of us? The electrocardiogram is a graph that represents the electrical activity of the human heart. The ECG is one of the mostly used diagnostic tests around the world, with around 300 million ECGs done monthly. Over 60% of those ECGs are misdiagnosed. Accurate ECG reading is a very rare skill that very few doctors are gifted at. My research question aims to answer why. Why do certain cardiologists are so gifted at reading an ECG image, while others are not? To answer this question, I used eye tracking, along with machine learning, to understand how do the most gifted doctors read an ECG image. To do that, I gathered eye movements data of hundreds of cardiologists from different heart hospitals and analyzed their movements. I found out that the most gifted doctors are actually the ones who interpret ECGs daily. Because of this repetitive process, they do develop their own personal system of efficient ECG reading. These human perceptual patterns are the added value of my research. Because of these, I was able to design an algorithm that supports and predicts the doctor's ECG reading with an accuracy of 92%. This algorithm is able to predict the doctor's accuracy across the 10 most common heart problems. Adding to that, my algorithm is transferable to any type of image, whether it is a medical one or not, including X-rays and, for example, like art images or even chessboards. The ultimate goal behind my research is to get rid of this 60% misdiagnosis rate and have ECG interpretation accurate all the time. In an era where the common narrative is that artificial intelligence is threatening the role of doctors, I see it as a supporting tool to enhance their performance. Because at the end of the day, the answer is always in the doctor's eyes. Thank you.
Thank you. This was really, really interesting. As someone with a history of irregular heartbeat and such, you know, I've seen a lot of these EKGs, and it's nice to know that you're working to help doctors to better interpret that data. So is this really about, first of all, wait, I forgot to ask you, I'm sorry. Tell us about yourself. I'm like so interested, I just want to like plunge right in. So first, tell us about yourself and how you ended up as a postdoc here.
I am Mohammed, and I'm originally from Morocco. I did my bachelor's there. I did my master's like between Morocco and Japan, and then my PhD in Qatar, the neighboring country, and then I came here.
Very international. Yeah.
Yeah.
So, and how did you get interested in this particular project?
Actually, I've always been interested in medicine. So although I did my PhD in computer science, I wanted to do something really related to medicine, and cardiology was something that I was interested in. I was taking classes like just for fun, like in Weill Cornell in Qatar. And I thought, why can't I combine between cardiology and computer science? So this is what I, yeah.
And so with this algorithm, do you then come up with a new kind of image that then the doctors more easily interpret?
So I can either come up with a simplified image, or I can just give hints to the doctor to look at certain places, because I use eye tracking.
I see.
Yeah.
I see. So you can kind of direct them to particular aspects of it. Yeah, it's so interesting to think about how there are different ways that people can use eye tracking, and you can learn so much about how people interact with, a particular environment like that. So it's really interesting to see it applied in this way, and I hope that you're able to really get to this point of being able to significantly improve people's experience there. So thank you very much.
Thank you so much. Thank you.
Yeah. Okay, that brings us to the end of our presentation. So at this point, I'm asking all of you to get involved and vote for the speaker of your choice. So all of you have a speaker's choice ballot. This is your moment to go ahead and check the box for the speaker that you think did the best job. The ballots will be collected by members of my staff. Ross will work on collecting the ballots. Okay, and now I would like to invite all of our speakers to come on up to the stage. Yeah, we got this. Just go ahead and line up. Move over, you guys. Okay, thank you. Yeah. Okay, the scores are in, the People's Choice voting is done, and it is now time for Q&A. But first of all, let's just congratulate these 11 scholars for all they've done. Yeah, and this is our moment for the audience to be able to ask their questions that came up for them across the talk. So who's got a question to lead us off? In the back, yes, please.
Really great presentation, thank you. I just have a question about the 3D printed organs. How long would it take?
What? Sorry?
How long would it take to print an organ?
Oh, so hello? Yeah. There's a different printing techniques. So there's like some of them will take days to print because they printed really layer by layer, and some of them now with the shining of light can print a big structure within like 20 seconds. Yeah, I had the same reaction when I read that paper. So, thank you.
Yeah. Yes.
Hello. I want to first of all congratulate all of you. You did a fantastic job, and I've been to many conferences and sat through many less stellar presentations. So very, very good. I want to just ask, what part of this process of preparing for today's Grad Slam was most beneficial to you?
I don't think the others will agree, but actually the last workshop with a theater professor, where we had to do very weird exercises, basically to get into the zone and getting our spirit animal out of us. But it actually helped because as scientists, we don't usually focus on that. We don't focus on the creative. So it was nice, and it was something different.
Anybody else? Yeah.
I do agree with you, Shaza. It was a bit weird when we had to do it because, telling scientists do something, not telling them how to do it is not really something you do. But I also thought it was really nice because he reminded us that it was really important for us to be more human because we're so used to dealing with hardcore facts. So making us be more personal and maybe a bit more vulnerable on stage was something very unnerving but also very useful.
Mm-hmm.
Of course, like the theater training was so beneficial, but also like the overall workshops, they really walk us through like how to tell a story. This is, I think for me, that was the most important part, is to try to tell a story like logically with using like a sort of a stream of conscious, quoting from Dr. Alia. I think that was like really beneficial to know how to actually like tell the story periodically. So I think that was really beneficial. So,
yeah.
So what actually touched me a lot was how to simplify the facts and not think that what we're saying is really might sound stupid to us, but it has to be very simple. So I had to like present my presentation to my son and see if he will understand it or not. Make it so simple. And yeah, that was also said from Alia's workshops. Thank you.
One of the things that really struck me was the power of metaphor. Because all of your talks, you use all these interesting metaphors and all of these different images, and how useful those metaphors were in helping us understand these really abstract concepts, but being able to interpret them in terms of something that we know and are familiar with, like a cat, for example.
I just want to add one last thing.
Please do.
Actually, the teamwork of our group at offices, thank you so much, and the teamwork of all the candidates here, because they give us very, very impressive comments and how to improve our talk, even if we are giving talks for too long to a lot of audience, but it was really helpful, yeah.
Yeah, excellent. Glad to hear it. Yes, question in the middle, right there.
Yeah, I have a question for Wajoud. You were talking about these crystals for the cancer cells. My question is, these crystals are targeted to certain cancer cells, or it targets all the fast-growing cells, for example, like the chemotherapy? Or it's just, it has a specific chemical structure or whatever that binds to a certain kind of a cancer cell, or not?
Okay, so that's a very good question. We've tested it with different kinds of linings, and we wanted to see which one will have the highest affinity to bind with it. To add to that, the coding that I was talking about, we actually functionalized it with something that's specific to certain linings, so we can actually change the target based on those functional groups that we place on top of the coding. Does that answer your question?
Yeah.
Okay.
Yeah, right here in the front.
Hello. I have two questions for Fayrouz. The first question is, does your material differentiate 50% humidity from 60, from 70 to 100%? And the second question, is it cyclable? Like how many times can you cycle the material?
Yeah, so with the 3 minutes, I was not able to get through all of the details of the work. But yeah, fascinating enough, it can differentiate between let's say 60, 70, 80 degrees, because it has a kind of a linear response versus temperature. And sorry for the second question.
And how many times can you cycle through it? So let's say you put it in high humidity.
Yeah, so
and
it is reversible up to as many cycles as you can think of. So it is fully reversible as well. Yeah.
Question over here.
Yes, for the rejuvenating livers. Yes. So you said that you have an effect when in aging liver you manipulate the epigenetics, right? When you knock out your protein. I was wondering, do you see an effect even in young livers? Do you see that they're messed up by manipulating the epigenome, or there is a way to do it in a healthy way also in the young?
So in the young mice, they are completely fine. So they are doing good. They are even doing better than the wild types, like the normal mice. So as I said, we see that when we change the epigenome in the young ones, we see enhancing liver regeneration. And those mice, we wanted to follow them while they age, and we actually noticed that they age like less. So all the parameters that we are assessing now, the activity, the thing, they look younger, and even in their cells. But yeah, it's still ongoing. It's a very new project, and we hope we're gonna find like more and more interesting results.
Excellent.
Yeah.
I think there's a question in the back.
I have a question for Kameen. How do you test the 3D printed organs which you print using a 3D printer?
Sorry?
How do you test the working of the 3D printed organs?
So we test them through their function. First, we test the viability of the cells, if they are dying or not. And then we do like immunostaining to check for specific markers there. And we do like RT-PCR change to test any changes in the cells. And lastly, we can implant them in vivo and see if they are making like on animals, see if they are making their function properly.
Thank you.
Thank you.
Looks like there's a question over here.
Hi, I have a question for Nadine. I'm not sure if it's, first of all, thank you all for your presentations. All the topics were very interesting. They're very intriguing for me. My question specifically is, I'm not sure if it's attainable yet, but can you target a specific bad gene you want to switch off?
A bad gene that we want to switch on? That's actually a good question, because any long non-coding RNA does not specifically target one gene, but there are several genes in a pathway. So, for example, Meg and Ryan, it interferes with pathways related to bone, not just bone diseases, but metabolism in general. So, it's not just one gene, it's several genes. So I'm not sure about the targeting, because this is like a different story and a different type of research. But I think maybe, I don't know, with the nanoparticles, you can target certain specific genes in the body. Yeah.
Oh, I see. Thank you.
You're welcome.
Question here in green.
Thank you all for your wonderful talks. It takes a lot of guts to get up on stage and present to a large audience. So my question is directed to Mohammed. Since you have like a lot of patient-specific information on these computers that you keep trackers on, I was wondering what the protocol for the permissions look like, because I'm sure it might be a tedious process. So.
Actually, it's not that complicated, because ECGs usually they are non-identifiable data. If you remove the name and if you just remove the name, you can even keep the age. The ECGs are non-identifiable. So usually, like more or less, hospitals and patients are usually ready if you tell them to provide their ECGs without their name. So usually it's collectible.
Yeah.
Thank you.
I think there was a question over here.
I have a question for Dev. So since your research is for astronauts, how would you create the environment of space while you're still on Earth?
So, is this on? Like, how do we simulate microgravity? So at the moment, we just do it at a cellular level. So we're trying to see like how these mechanisms work at a very small level. So we have systems on campus where you could actually simulate that. We have a system called the RPM, a random positioning machine, where it sort of basically rotates in 2 different axes to mitigate that gravity vector. So you're able to remove that whole vector and then simulate it. And you could even change the settings to make it simulate Mars or the moon.
Wow.
So it's a quite cool system. Yeah.
Uh-huh.
Firstly, I would like to congratulate all of you for such great presentations. So I have a question for Kompil. So you mentioned Isaac technology for 6G. So how exactly are you planning to use that narrow spectrum for multiple applications?
So it's not actually a nanospectrum. It's part of the electromagnetic spectrum that's used by cellular. It's used for cellular communication right now. So you know the electromagnetic spectrum is limited, right? Like it exists in nature. And there's only a part of it that we use for communication. So that's the problem of like scarcity of resource. And our wants, our needs are just growing. So like we're constantly trying to look for ways to like reuse the spectrum. We also have in 6G, like another direction is that they've delved onto like millimeter waves, which gives us more bandwidth. But at the end of the day, like, the spectrum is finite and our wants are growing. So we have to find more ways to reuse it.
Shed some more light on how specifically you are planning to reuse the spectrum?
So we're trying to use, so currently the same spectrum is used for sensing and it's also used for communication. But they're used separately. Like, the applications for sensing are doing their own thing, like radar and all of that, that's separate. And like your cellular communication is separate. So what we're trying to do is we're trying to put both of them in one system. So like one base station is going to do both communication and sensing. That's kind of like the basic idea behind the technology.
That makes sense. Thank you so much.
Thank you.
So I was wondering, with everything that you've learned through this process, how do you think that you will, to what extent will this change your own practice, either in terms of teaching or in terms of research or in terms of when you give presentations in the future, regardless of whether it's a kind of at a scientific conference or at another venue? What do you think?
So I think overall, this experience was such an eye-opening experience because it forced us to actually think of some kind of applications, even though on the laboratory levels, we are not required to think of the applications or the futuristic aspect of where our material would be applied. But it is nice because it helped us to think of that, and I think moving forward, I would want to think about the impact before even starting new projects. So I think it was really inspiring.
Yeah, that's something. That's something. Anybody else? Yeah.
Yeah, I would like to add that also it taught us how to tailor the presentation for a specific audience. So now we did it for general public, but also if we're going to specialized conferences, sometimes we think that some stuff are taken, some words or some ideas are taken for granted. And in one field also that's not true. Some people might know this fact, some people might not. So we always try to explain stuff in a simple way as well as add what you are really doing.
Yeah, I'll just add to that back when I was at the University of California, I was an associate dean, and one of the things I had to do was interview candidates that were coming in for faculty jobs. And I was, one of the things when you go to these big interviews, you're there for a few days and you meet all these people, including one of the deans, and I was one of those people. So I would be sitting down with people who were talking about, who were in fields that I knew nothing about, like labor history or something like that, which has nothing. I'm a linguist. It was just nothing I knew anything about. And so being able to talk about your research to people at that level is also really important. Even as you go up for academic jobs, assuming that's the direction that you want to go, even the ability to be able to do this within the academy is important. And how many of you do work that you think of as interdisciplinary? Yeah, several of you, so that when you're speaking to other people and needing to explain your work and your discipline to others, the kinds of communication strategies that you've been learning here are things that can then facilitate that process. And one of the things we need to do with interdisciplinary work is learn how to talk about our discipline and recognize how our discipline works, because disciplines don't all work the same, and there are different assumptions, and being able to understand those assumptions and communicate them is also something that's important. So hopefully, with time, that'll be something that you'll get engaged with and notice the impact of this. Other questions? Yeah, there's one over back here.
Hi, can you hear me? Yes. Okay. My question is for Shaza. great work, very promising. But I just want to ask, how do you stimulate antibody production if you're not exposing the cells to produce specific to certain antigens? Like compared to vaccines, you're introducing inactivated virulence factors. So how would you do that?
So for vaccines, we know that we put weakened viruses or bacteria in your body. But with the chip, we are going to actually put the real virus or bacteria, and since it's outside your body, your cells that are in the chip will get activated and work as if they would work inside your body if you got infected. So that's how they will get activated. And also, because we have it in the lab, if we want them to produce something more specific, we can add activators that we produce directly to the chip. So we can regulate it as much as we want.
Further questions? Yes, here.
Thank you all for great presentations and making all this effort throughout the last few weeks. So I'm sure you all have given a lot of presentations throughout your scholarship. So I was trying to understand, how was this experience different from those presentations? And are there any things that you did during this presentation that could be transferred to those, let's say, more academic style presentations at conferences?
I think this kind of presentation compared to a scholarship one is like way more funny. I mean, we take pleasure to do it and to find with our family some metaphors that they can actually understand. And you involve so many people inside your, world of science. So yeah, it's way much like funny, I would say. And also it helps at both sense, as I don't know who said that, but just thinking about the impact, like the long-term impact on all the world that we can do is like very helpful for all of us, I think. So yeah, that's.
Anyone else? Yeah, Lyle?
Yeah, it's working. Yeah. So this presentation is a little bit different than all the other presentations because it's everything that we do in like a year and a half or like 3 years, and sometimes it's longer, like the whole PhD or like for 4 or 5 years. You try to summarize it in literally 3 minutes. And I tried to sell you my project, and I tried to make you feel the importance of it in just 3 minutes and make you appreciate it, and appreciate also the effort that we put in the presentation, coming up with a presentation that not just it's tailored for you, it's tailored for everybody. And we all come from a very different background, so it's very challenging. You can be standing in front of an audience that 500, but they're all scientific and they all understand the certain topic that you're talking about. And you're not going to feel as stressed as we feel right now. We come here, and everybody comes from very different backgrounds, so it's very challenging.
I think another thing is that over here, you're trying to keep people focused, because it's not relevant to them, they might lose their attention. So it's more focused towards that. But I think that is something that we can take on and as a skill and use it in our even technical presentations, because when you're at a conference, not everybody is an expert in that exact thing that you're working. So if you make your content more relatable, more people will take away from your talk, I think.
One more thing I would say is there's also something called, in the industry, which is like a 30-second pitch or 1-minute pitch, where you're trying to get basically the person to hire you. So I think this is really good practice for that, because you kind of identify the main points that are important and what you can give them that no one else can. Also, I think it really makes for a memorable talk. I mean, the majority of the talks that I remember from conferences or classrooms or something are professors who started with the basic and then just built up on it and assumed that we didn't know anything about the topic. We probably didn't, but yes, they basically just assumed you didn't know anything. So these just make it easier for you to understand, and it allows you to take a step back from, because whether we like it or not, when we're spending so much time day in, day out, on the same thing, it gets so easy for us to get like a tunnel vision. So when you take a step back and be able to explain it, you might actually come up with fresher and newer ideas.
So I'm curious, for a 3-minute talk, how many hours did you put in to get to 3 minutes?
We can't reveal this because our PIs are here.
It's interesting, though, to think about, even just for a regular, say, 20-minute conference talk, how many hours go into this one 20-minute period. It's sort of like cooking a big holiday feast or something, and then it's all gone in half an hour when everybody sits down to eat. But takes a lot of time. Okay, further questions? Yes.
Thank you. I have a question for Mohamed Tahri. If I understand correctly, you want to advise where to look at for doctors when they look at those graphs. Do you think it's also relevant to look at your data as time series to understand and to find anomalies through the time series instead of looking at the eyes of the doctors too?
Yes, so the eye tracking was the first step. Actually, I was planning, the story is that I was planning to use the time series first, but I realized that the data is so complex and there is a lot of noise that I decided to go the other way around. Yeah.
Thank you.
Other questions? So I'm curious as to how many of you really are interested in primarily staying in academia, and how many of you are more interested in careers outside of academia, and how many of you think about potentially moving back and forth, which is a pattern that I think is becoming stronger as the years pass.
So I've graduated from pharmaceutical sciences, so I've tried working at Pfizer when I first graduated, which is like the biggest pharmaceutical company.
Yeah.
And I did not enjoy industry, particularly in the Middle East. There's no R&D. So I enjoyed more academia, and I think that's the career I want to pursue. Yeah.
So looking for faculty jobs.
Yes, definitely. A bit of research and teaching together.
Yeah.
I enjoy also presenting and teaching.
Yeah. Others?
I think for me, it's always been academia as well. I did an internship in industry, and although I interacted with many people, it was very boring to me and not fulfilling. So yeah, I still have to finish my PhD first, but I really look forward to teaching as well.
I think there's like a sweet spot when you have a collaboration between the industry and academia. So that's kind of where I would want to be, so that you have the freedom to do like quality research without being pushed, because time is money in the industry. So you have time to make quality research, but also be able to translate that into something that can actually have proper applications. So I think I would like something that's a mixture of both, in a way, like maybe consulting or something like that, like a collaboration.
So what about entrepreneurship? I mean, a lot of you are making these amazing discoveries and thinking about how to apply them in a very direct way for these concrete results. Are any of you thinking about potentially starting businesses, getting patents, and really moving more into a kind of entrepreneurial role?
Yeah, so for our lymph node on chip, we would like to eventually actually get it on the market. And it would initially be used in the lab, but we can maybe somehow make it to be used at home as well. So people can maybe use a prick of blood or saliva or etc.
And then just self-inoculate themselves in a sense. It's not inoculation.
Exactly.
I don't know the right term, but that'd be amazing.
Yeah, I mean, especially in third world countries where we saw in COVID, it was a big issue of getting vaccines to them.
Right.
So, yeah.
Right. Well, did you?
Sure, I'm also fond of the model where you start something in academia and you can take it to the next level and you can have a spin-off startup from that from academia. So something like this in the field of malaria, or something that that can benefit many of these children that get affected by the disease. That would be great if we can patent something that we find in the lab and take it to the next level and have, start that model of business. That would be great.
Yeah, I hope it works for you.
Thank you.
Yeah. Okay, well, I see that people are filtering back. That means at this point, let's give a final round of applause to all of our presenters. And I'm going to ask you all to please go and have a seat again.
Would you like a
You can, sure, or you can just set it on the table over there. All right. So before I announce the winners, I just wanted to point out that an event like this takes a lot of people to really produce it. And I think we have a slide on this. Yes, it's already up there. Okay, first of all, I want to really give a heartfelt round of applause and thanks to our wonderful judges. I know this is really hard to judge these talks. Yeah, I mean, when all of the presentations are that good, you know, it's just really, really hard not to just give everybody perfect scores. So, you know, thank you for all your hard work and for your contributions. But we also wanted to say thank you to all of the other groups that have been helping us here, such as the Office of External Relations that's helping us with, you know, social media communication, all of our tech group here, from our audiovisual services team, the guys in the back booth, and the guys with the microphones. Let's give them a round of applause. And you've heard about these wonderful workshops, and we had these volunteers come in and be able to teach those workshops for us. And so Linda Mubarak, Alia Soliman, and Robert de Guzman, you know, it was obviously so useful for so many people. So thank you for that. And then, of course, our postdocs and grad students, not only these ones, but all the ones that were involved and contributed. So we're really grateful. So, but an event like this, most of all, I think is done by my wonderful team in the Graduate and Postdoctoral Programs Office, who have put in months of work, literally pulling all of this together. And so I just really wanted to give my heartfelt thanks to my team, especially Ross and Elise and Carl and Ken and Aisha and Yvette and Magdalena. I mean, it really is a group effort, and I couldn't be prouder than I am of my staff. So I think I'm just so impressed. All right. The envelopes, please. All right, here we go. Okay. Your choice for the best of the Grad Slam talks for 2023, the winner of the People's Choice Award is Devjoy Dev. Congratulations. Okay, why don't you just stay up here on stage? Okay. Now for the selections by the scorecards, by the judges, we have two, one for the runner-up and one for the grand prize winner. So beginning with the runner-up, the winner of the runner-up prize for 2023 is Yusra Ajwao. Congratulations.
Thank you. Thank you.
Yeah. And now the moment we've been waiting for, my hands always shake when I get to this point of the process. The grand prize winner of NYUAD Grad Slam 2023 is Kamil El-Khoury. Congratulations, that's wonderful. I'm so happy. So here we go. Let's get them all decorated up here with everything. Oops.
Okay.
Here, I'll hold this one. Yeah. There. There we go. Okay, got it? Got it? You're not going to drop it?
No.
Okay. Okay. All right. Well, thank you all once again for being here, for supporting our graduate students and postdocs.